We are Team Airbenders.
Our goal is to design an all-electric general aviation aircraft. The figure on the left shows our analysis of several NACA airfoils on X-foil. The green line shows the NACA 4415, which was our selected airfoil. You can see that the curve has an extremely high CL over CD, which increases lift. It also has a very high lift coefficient for increasing angle of attack. The right figure shows the pressure distribution of our airfoil run on X-Flyer 5. Our team used benchmarking to determine the initial guess of 151 square feet for the planform area of our wing. We decided that we wanted a large aspect ratio to increase the lift of our wing. The table below shows our optimum wing size. Smaller wings provide more lift but also increase drag. We decided to choose a middle point that would minimize drag while maximizing lift. This chart shows the change in various parameters as we increase the lift coefficient. As the lift coefficient increases, so does the drag coefficient, so we cannot simply choose an extremely high lift coefficient for our wing. It is also unrealistic to have such a small wing at these high lift coefficient values. Our wing is better than the competitors due to its high aspect ratio. This allows the wing to generate more lift with the same amount of thrust and power. Since we are extremely limited on power, our wing must generate as much lift and as little drag as possible. This slide compares several aerodynamic parameters of our aircraft to two other aircraft. Compared to the Cessna, our aircraft has a higher aspect ratio, allowing for more lift, a larger CL over CD, which reduces drag, and a larger wing loading, allowing for more stability and speed. Compared to the Unique, our aircraft has a smaller aspect ratio and CL over CD, so less lift is produced, but our design has a larger wing loading, allowing for faster speeds. Our aircraft will also be able to seat 4 people, while the Unique only seats 1.
Our aircraft requires an all-electric motor, which narrows the selection of motors. The motor must be lightweight and generate large amounts of power. The engine needs to be lightweight because we must also account for the weights of the batteries. Our team focused on engine's power density values during our down select to ensure our engine is lightweight and powerful. From previous battery down selection, our group chose to use a lithium-ion polymer battery to power the electric motor. This motor will be connected to one simple probe. Our team decided to have only one engine to keep the weight low. The battery and the motor are not powerful enough to overcome the weight of 2 engines. Another engine would also greatly increase the drag because of the configuration required of 2 engines. One engine can be integrated into the nose of the aircraft, whereas 2 engines must be mounted onto the wings, thereby increasing drag. Our team narrowed down our selection to 5 engines that fit parameters of our design. From these 4, our team compared weight, power, efficiency, and power density. From the data collected, the Siemens motor is the most beneficial to our design. It has a low weight and extremely high power density compared to the other motors. The Siemens claimed that the motor will be able to lift a 2-ton aircraft off the ground, which is approximately the weight of our aircraft. Lithium-ion batteries are rechargeable batteries in which lithium ions move from the negative pole to the positive pole, therefore creating a current. The current produced by the lithium ions movement powers a motor, which then turns a prop. Lithium-ion batteries are considered clean energy and have no hazardous byproducts. Since our aircraft is all electric, we do not need to worry about the fuel mount or placement. However, the placement of the battery is still of importance to our design. Our group decided to put the battery near the center of gravity of the aircraft so that the battery does not affect the moment about the longitudinal or lateral axis.
So for the materials portion of our structural analysis, we started with an analysis of couple of different materials, including aluminum, carbon fiber, titanium, and steel, and leaned towards the end towards aluminum and the carbon fiber composites, mainly for their strength and cost, as well as manufacturability and weight were our main two. Comparing aluminum and the composites, the density of aluminum is around 2.71 grams per cubic centimeter versus carbon fiber at 1.7 grams per cubic centimeter, which using the carbon fiber would then give us a 60% weight decrease using those. So we leaned more towards those. Some of the benefits of the composites were its high stiffness and modulus of elasticity, its high strength, as well as its good corrosion resistance. Now for the aluminum, we could easily put some epoxy on that for the corrosion, but overall the carbon fiber gave us a much lower weight, as well as those extra added benefits. As far as the layout of those materials go, we didn't want all carbon fiber because that would get pretty costly, especially because aluminum is much more easily manufactured. And so we chose aluminum for our main body of the aircraft, and carbon fiber composites for the wings, as well as the horizontal and vertical stabilizers. For the structural loading, we considered all loadings, but a couple major loadings we more heavily looked at were the wing loading, including the lift distribution, as well as the weight of the wings and all the components inside of it. Also our N factor, which will be covered later in the VN diagram portion. For the wing loading, as you can see to the right, is a graph of our lift distribution curve, the blue line being the elliptical loading, as well as the red being the trapezoidal, and the green, which is our average lift distribution curve. And below that are the shear and moment distribution loads and their weights. We ended up calculating our total weight to be around 100 pounds. And then using these graphs and those numbers, we're then able to build and design our struts and wings accordingly, also using our carbon fiber composites in those wings to be able to support that.
So here we see the first little bit of the systems that are going to be used to control our aircraft to ensure safe flight. The main component of the plane systems are the rudders, which control the yaw, the elevators, which control the pitch, and the flaps, which are used to control the roll of the airplane. These components are all used by the pilot as a means of steering and controlling to create a stable aircraft. Also considered to be part of the systems is the payload of the aircraft. For a smaller aircraft such as ours, the only payload that the plane would be subjected to is the weight of the passengers as well as the weight of the fuel. In our case, the weight of the fuel is to remain constant throughout the flight, as we are using batteries as our fuel, and during flight batteries don't become burnt off such as regular liquid fuel does. All the weight of the passengers and the batteries should be located in this small cabin towards the nose of the aircraft, almost directly under the wings. The picture to the right clearly shows where not only the payload should be found, but also the location of all previously mentioned systems of control.
This slide shows our design's VN diagram. The purpose of the VN diagram is to show at what conditions our aircraft can maintain flight. Notice that our aircraft is not limited by the gust loading or the stall region. The main limiting factors is the stall limit, corner velocity, and structural failure region. The program provided by Dr. Jacob outputs data for given criterion. Our aircraft stall velocity was calculated to be 182 feet per second, the corner velocity was calculated to be 203 feet per second, and the max speed was calculated to be 334 feet per second. All of these values were calculated at an altitude of 3,500 feet.